Okay, let me share my screen. Do you see my screen?
Yes, whiteboard.
Okay, so you have 10 solution, 10 particle.
10
B1,
particle, yeah.
B2,
Up to, yes.
B10. Each solution, طبعا this is the position. These are the optimized parameters embedded here. Yeah.
Yes.
Up to XM. So, and each particle has its objective. So you substitute with this optimized parameters in the objective function. So you calculate J1, J2, up to J10. Okay?
Yes.
If this is the initialization step, you consider this position as the particle best or local best as well. Okay? So all these are local bests at the same time and the position of the particles. Of course, you can come to these objectives and search for the minimum, which gives you the global best.
Yes.
And this is at the same time as the best solution. Okay? One of those would be the best solution. So this is the initialization step. You have velocity for each one, V1, V2, and so on. So when you go here, you update the velocity and you update the position. Having this is the local best for particle number 1, and this is the global best. This is the particle best for the particle 2, and this is the global best, and so on. You have only one global best and 10
صوتي راح يا دكتور.
صوت راح. Why? Are you hearing me?
If in some...
I can hear you.
Is it okay now?
Yes, we can hear you, but go and come back.
We can hear you, Doctor.
Okay.
Okay. So when you update the velocity, and
then you, Doctor. Doctor?
Yes.
Updating the velocity and the position, we will get another 10 solutions from B11 to B20.
No. B1 B1 to B10, Bob.
B1 to B10, the new one. Okay.
Yes. B1
the new position.
New position.
Yeah.
خلينا مثلا نقول this is okay. This is the new positions, and again you can calculate J1 up to J10. Now here you do two things. You compare this G1 or J1 with J1 here.
Yeah, that's my question.
For particle 1, and you can see which one is better, and you can update the local best accordingly. If this position is better, if this position,
always we are comparing one by one that we created from the parent, and we replace it if it is not if it is better.
We are not replacing. We are replacing the local bests.
Only.
Yes, we are replacing only the local best. If this is J1 is better than J2, this J1 is better than J1. If this position is better than this position, then you update the local best and you keep the particle as it is. Particle, we are not replacing the particles. We are not replacing the particles.
Now it's clear. Yes, now it's clear. That's why I was confused in this one. So it's mean we update only the local, and then we keep the particle, and we start to move from that position.
Exactly, from that position, but having the updated local best. Maybe this one, maybe this one.
Now clear, doctor.
Again, you have here the global best. One of those would be the global best. And this global best would be the best solution in this swarm or in this population. So you compare this global best with the best solution found so far. خلاص, this will be considered as a global best. Okay? So this will be considered as a global best. Now we compare this global best with the best solution found so far. And then you can update the best solution. This is what we are looking for. We need to find out the best solution. So if this better than the best solution, we update the best solution. Otherwise, we keep the best solution as it is, and we move forward to the third iteration. Again, particles, you update the velocity, you update the position. You have here 10 particles, you calculate J1 up to, you compare this J1 to which the better one here, which is the local best considered so far, and then you can update the local best accordingly if this is better. Otherwise, you keep it as it is. And then you repeat. You have here the global best, and you compare with the best solution found so far, and you update the best solution, or you keep the best solution as it is, and so on. We are not replacing particles.
Okay.
Here.
Yes.
Okay.
Clear, doctor. Clear.
Okay. Great.
Thank you very much, doctor.
Since you are discussing this, and I have posted homework number 4 on particle swarm. This is straightforward. It doesn't take much time. You have here. Do you see the MATLAB?
Yes, we can see it.
Yes, doctor.
So in MATLAB you have here like a particle swarm function. It's called the particle swarm. So similar to GA in this optimization toolbox, and then you can have function, number of variables, and boundaries, constraints, upper bound, lower bound. You can go and check this, and you can easily solve the problem that we given in homework number 4. It doesn't take any. I think it will not take much time. We just have few lines here in the function itself, and that's all. Okay, so MATLAB also make our life easy. So we can go out of this.
Doctor.
Yes.
There's just a quick question here regarding the quality inequality constraint that we saw in the homework, the quality constraint, but again the concept of adding this equality or inequality to the not to the tool function or built-in function. If we want to develop it from our side, like or if we want to code it, how we can add this to the function itself? We try to search about it, understand it from different sources, but it's still not clear. Because what we found, some of them addressing like a simple approach, like a penalty function, like satisfying all the condition or constraint, that's mean apply the function. Otherwise, you penalty this objective function with a large number. This is a simple approach, they call it. Some of others, they use like what we had in the earlier stage of the course, the optimization, I mean the Lagrangian approach. I'm not sure about the others, but there are several methods. I think it's like a developed approach, but which one should we go with? And which one should address like
well,
the minimum?
You have two approaches, two simple approaches, let us say. There are a lot of techniques for handling the constraints, if there is any violation. But let us take the very simple two approaches that we have. The first one, as you pointed out, the Lagrange multiplier. So you augment the objective function to be equal to the actual objective function plus penalty terms. Penalty terms in terms of lambda multiplied by x minus x violated limit x max or x min square مثلا. If you have any violation. طبعا this is if x1, and if you have also another variable x1 minus x2 or x2 minus x2 minimum or maximum. We have here which violated limit. Maybe you violate the minimum or maybe you violate the maximum. This could be dynamic. The value you'll use here is either the maximum limit or the minimum limit, depends on x1 violates which limit. So you can have here a penalty terms, okay? So you can incorporate the constraints here. The second is to do the following. You create new solutions, and then you check whether this solution is feasible or not. Are feasible or unfeasible? Okay, they are belonging to the search space here. By the way, they can belong to the search space, but your problem is complex, and you have to check some other. It's not only the limit of x below, and no, this x could affect some other variables here, and you need to check these variables. It's not directly given in this x, but you need, for example, voltage, speed, or whatever. You need the voltage to be, for example, less than this or greater than this. So this voltage, in order to get this voltage, you have to solve some algebraic equation, and you have to in power area on electrical engineering, they can know about the load flow. You have to solve the load flow problem in order to get these voltage. So you have to run the model of the plant in order to get this value, and then you can see whether it is feasible or not. So what you are doing is you have here several particles. This is valid for any techniques, and it could be particle swap or whatever. You have here some solution, for example, and then you write. Of course, you have to write the model, and this model you have to solve your differential equations or algebraic equations. You have it here in the model, and then you calculate any variable that you need to check, and check this variable whether it is within the limits or not. If it is within the limits, that means the solutions here is feasible, and you can continue to calculate the objective function corresponding to that solution. Otherwise, you remove completely this solution if it gives you unfeasible solution at the end, and then you can start randomly, or you can fix this. For example, you can move around it, or you can play with the variables, or you can eliminate it completely, and you start one random solution. So this is the way. Either you incorporate it here, or you check, and if it is unfeasible, eliminate it or discard this solution and start with another solution.
But so, Doctor, for the second approach, like whether it is feasible or not, here we are talking only about the bounded variables, we can say. But when we said that we have like inequality constraint, for example, like x1 plus x2 greater than or equal like certain number. So how can we adapt this?
Whatever, any variable, V1 is calculated through the model here, and V2 also is calculated through the model. So if you have any constraints, V1 plus V2 is lower than this. So when you solve the model based on this particle or based on this solution, you have all the variables found here. And then you can see whether this constraints that you have is satisfied or not. So once you solve the model, you can check all the constraints that you have.
So if it's satisfied, that means we continue, we take it and calculate the J. Otherwise,
calculate the objective function. This is feasible solution.
So otherwise, we neglect that. We
yes, you eliminate this solution and create another solutions. Sometimes they divide by 2. Sometimes they set up the violated limits. So there are several ways to fix it. If you are interested, you can see the literature in this regard. But this is the very simple ways to do it. Either you incorporate it here as a penalty terms. If you have any violation, like a voltage here, مثلا, you solve the model and you get V, and if this V is minus V max or V minimum, max or minimum, it depends on how much V will be lower than 0.95 or greater than 0.05. So you get the reference here, and you have this is a scaling factor, and this is a square here. So this is the penalty term. So you set it, for example, if J actual in the range of 100 مثلا, and this voltage is in the range of 0.1. So in this case, you have to multiply here by 1000, for example, to get the within the same range. Sorry. Okay, Fauzan?
Yes, clear.
Okay.
Any other question? If we can take an example in this issue, maybe it will be more clear for us, because I have the same issue. I try to write constraint equality.
Example
in this, how can we add equality and inequality constraints?
Okay. Sometimes if you think مثلا for example, if you have equality constraints, let us say, you have مثلا minimize x1 square plus x1 x2 square plus مثلا 3x3 square x1 x2 whatever. And you have like bounds for x1, x2, x3, minimum, maximum. So usually if you have, this is very simple to satisfy these equations. And you can generate randomly any value between the minimum and the maximum. So you assign x1 and x2 and x3. And then you have another constraints, مثلا x1, x2 and x3 equal to whatever, مثلا 100 or whatever. Okay? So what you can do is you can start randomly to generate x1 and x2 and x3 and substitute here. Once you create, substitute. If this condition is satisfied, but this is a feasible solution, so let us consider it and go and continue. Otherwise, you have to create randomly again and again until you fill the population with the feasible solutions. This is one way, which is not like this is what we call the brute force يعني approach. يعني فيها نوع من يعني ايه يعني it is not intelligent way to do it. If you think about it يعني deeply, you can say, okay, and I will generate only x1 and x2, and then I will write x3 right away equal to 100 minus x1 minus x2. So I am quite sure that this will be satisfied. Okay. So this condition will be satisfied. Most likely will be satisfied. Let us be precise. Most likely will be satisfied. I will not generate x3 randomly, but I will calculate x3 based on x1 and x2. So I'm quite sure this solution of this constraints will be satisfied. Okay. So this is one way, and you can have, if you think deeply, and you have, if you have a specific problem, and you are fully aware about the problem and the constraints and the problem formulation, you can maneuver here. You can, even for implementation of the crossover and the mutation, you may have, when you do crossover, you may have violated, or the solution becomes unfeasible solutions. So the way of having this crossover right away in this way, maybe will give you, will violate the, or will destroy the feasibility of the solutions. So you have to do the crossover intelligently. And this is very important in a scheduling problem, as we pointed out before. In a scheduling problem, any changing in the activities and the dependence of the activities must be observed, and with crossover and mutation most likely will be destroyed. The feasibility will be destroyed. So you have to think about doing a crossover and the mutation in a more intelligent way to minimize the unfeasibility solutions that comes out. Is it clear, يا حماد? ولا هشام
Yeah, it's clear, but actually my concern is that what if I have multi-equality and equality constraints? That will make it more complicated. Am I right?
Yes, of course. And this is a simple example. This is direct. طول x1, x2, x3. And if you have more, then the problem becomes more involved. Yes, you are right.
Okay.
I agree with you.
Okay.
But
Clear,
you
thank
know, and again, and I would like to emphasize on look at the problem and think about creating feasible solutions in more intelligent ways. Okay. So usually some way you have here, for example, if you have very complex system, it becomes very difficult even to find a feasible solution. And to find a feasible solution, it becomes very difficult. And what you can do is, this is one approach that I personally used it. And I will use this one. And I will apply some of the local search technique. Local search technique similar to, for example, simulated annealing or taboo search. This is local search. I start with one solution randomly, and I'm quite sure that this solution is unfeasible. So I have here some penalty terms, and I start run about 10, 11 or 20 iteration on this. Once I have G augmented and J augmented function equal to the J actual, معناها انه all the penalty terms are diminished, and in this case I reach to a feasible solution. So this is some kind of pre-processing, preparing the feasible population here. So you start with any solution randomly. The solution for sure will be unfeasible, and I will carry out 20 iteration with this very simple techniques. It doesn't take much time, and you are handling only one solution, which is unfeasible, and you search here and there until you end up with a feasible solution. If J augmented equal to J actual, the solution becomes feasible, and I count it here the solution number one. And then I move for another current solution, and then I start doing minimization until I reach to the feasible solution S2 and so on. And I continue until I finish the population. This is also another way to do some preliminary calculations for feasible solutions. Is it clear, Hisham?
Yeah, clear. Thank you, Doctor.
This, Doctor, is this kind of, for example, seems to me that we are generating the population, and then before we start our let's say minimization of the function, like we can do this like as we are doing two minimization problem in one code. Like the first one is to sort.
You have here pre-processing. This is the optimization problem here. This is the main problem.
Yeah.
This is the main optimization. And to generate a feasible population, you do some local search techniques, okay, and then you have this population filled by feasible solution here, and then you start your problem. The objective here is not to minimize. The objective here is to have J augmented equal to J actual. That means in all constraints are satisfied. Is it clear?
Yes.
And of course, you will not calculate this And all these terms, by the way, all these terms will not be calculated unless we have a violation. And it is not for all variables x1 we will calculate this. No. If x1 is greater than x max, we will calculate this term. Otherwise, this term will be 0. If x2 less than x minimum, we calculate the difference and the difference square, and then we add this to the actual objective. Otherwise, this term will be 0. If x1 between the limits, so this will not be calculated, and so on. And these terms will not be calculated for all values. Is it clear?
So this means I have to check each term also in this penalty equation.
لا انت انت you have x1, you create x1 and x2 and x3 and so on, and you solve the model and you get other variables that you need to have bounds here, right? So if any variable violates, then you calculate the term here. B1 violate, then you calculate. B2 doesn't violate, so this is 0. B3 and so on. And you add all this, and then you put it here with the objective function. When you calculate the objective function here for any solution. Is it clear, Fawzan?
Yes. Now clear.
Okay. If anyone has a specific problem and he wants to formulate it, he can consult me. We can discuss, but maybe not during the class, but during the office hour, or we can arrange for any specific problem. Let me understand the problem, and then I can help. Okay. So let us continue the simulated annealing. We already started the simulated annealing. By the way, we have a quiz, as I mentioned, and I made it automatically will appear in a few minutes. So be ready for this. It's just 5-minute quiz. Very simple, straightforward. This is the annotated version or not? No, this is not the annotated. We can go and open this annotated version, yes. Okay, so we finish all this definitions and process. I think we stopped here last time. As we mentioned earlier, this simulated annealing algorithm is or mimics the physical process, annealing process. We start heating up the material until we reach to the melting point, and then we start cooling in steps. And at each temperature level, we will keep the material until we reach to, and we heat up here, and then we start decreasing in steps. And at each temperature, we will keep the material for some time in order to reach to the thermal equilibrium. So and then we cool down the temperature, and then we move to another level, and we will keep it until we reach to thermal equilibrium and so on. So we discussed the analogy of the simulated annealing algorithm with the annealing or physical annealing. And we reached to this point where we need to, in steps, we can see the simulated annealing algorithm. In simulated, طبعا احنا of course I don't want to come back to this acceptance ratio and the acceptance criteria and so on, current solution, trial solution, and all this already covered last class. In simulated algorithm, each candidate طبعا has m-dimensional, and it's, simply it is a solution, so it is a vector of the optimized parameters. Step one is initialization. Set the initial value, and we set the initial value here. Now, here we will start heating up at the beginning. We will heat up at the beginning. We will start with very small value of CB0, and then we generate randomly an initial solution. So, and I would like to emphasize on, the simulated annealing is not global search. You don't have 10 solutions running together or 100 solutions running together. You have only one solution. So this is called local search. So you have one solution and you generate another solution and you compare and so on. I think the quiz is appearing now. And if this is the case, so we can stop and do it.
Should we start now?
Yeah, if it appears, then you can start right away. The quiz will disappear in 2-3 minutes. So you have to start as soon as possible. Okay, so let us continue.
Can we see the answers, doctor, for the quiz?
Not now. At the end of the class, I will release it, inshallah.
Okay.
Okay, so initialization step, we will heat up the material. We'll start with very low temperature. CB is corresponding to the temperature. And we generate randomly an initial solution. For our problem, you have here K, T1, T1, T2. So the solution could be 33.9 and 0.1, for example. So this is the initial solution. Okay. X initial, okay. The parameter XJ, of course, between the limits of, usually it's not an issue now to create a random solution if you know the bounds. And you can calculate the initial objective for this initial solution. And we set this initial solution as a current solution. So this is our current solution. And at the same time, we will consider it as a best solution also. And this is that initialization step. Let us see. So it's current equal to X best and equal to X initial. And again, also the objective is the same. So this is the initialization. You have only one solution. Step number 2, create trial solutions. Now we need to, in order to start cooling, we have to reach to high level of temperature. So we will heat up. So we will check the acceptance ratio as we discussed last class, N2 over N1. We will create, for example, 100 solutions, and we will see how many solutions will be accepted. So this ratio, we need it to be approximately 1, very close to 1 in order to start cooling. So we will create trial solutions, and within the neighborhood of the current solution. We have a current solution here. We can search for a trial solution in the neighborhood of the current solution. We will generate 100 trial solutions here. طبعا النيبرهود دي of course calculated as similar to the Vmax of the particle swarm, and we detailed how to generate the trial solution within the neighborhood here. We calculate Dmax for each dimension of K, of T1, of T2, and then we can generate random variation and add to the current solution, and then you can have this randomly generate N1 of trial solutions in the neighborhood of the current solution, and check how many of these solutions, check the acceptance criteria for all trial solution and calculate the acceptance ratio. If the acceptance ratio is close to 1, then we can, خلاص يبقى this is, we reach to a very good or very high temperature. Otherwise, we need to increase CB0 by multiplied by alpha, where alpha is greater than 1, to go to higher temperature level here. And we will continue until we reach to the acceptance ratio, N2 over N1 is approximately 1. So go to step 4, else multiplied by alpha, alpha is greater than 1, heat it up, increase the temperature. And then go back and forth. Go to step number 2, generate trial solutions, generate N1 trial solutions, and then you heat, and then you check the acceptance ratio, and then you go back and forth until you go to step 4 if the acceptance ratio is close to 1. Then we will start looping now, start cooling now. Looping or cooling, we start cooling here in this. We start decreasing this CB by CB equal to CB times mu, and this mu is less than 1. So we will start cooling. We can set the counter now, it becomes 0, and we will start decreasing now the temperature. So the chain counter or the iteration counter equal to 0. And then you can update the current solution. So the current, generate a trial solution within the neighborhood of the current solution. And if X trial satisfies the acceptance ratio, then you consider X current equal to X trial. You replace X current by X trial. You have here X current. And then you found here X trial. X trial is better. Then this becomes X current. And then you, around the neighborhood of X current, you generate X trial. And if X trial greater than the X current, then you put it as X current, and you move here and there in this neighborhood. So you consider X trial or X current equal to X trial, and of course you calculate the objective, and you keep X current equal or J current equal to J trial. And if you accept it, then you can check whether J current is better than the best solution, J best or not. And keep in your mind, then we are trying to find the best solution. So this solution now, new solution, so we can see whether this is better than what we have so far or not. So go to step 6. Step 6 is updating the best solution. You have to check it here. If J trial is, this is minimization problem. If J trial is less than J best, then you update the best solution. And then go to step 7. Else, if it is not better, then we go to step 7 without updating. So else we go to step 7 or the next step without updating. So we will check now the equilibrium. And you have X current, and then you generate X trial, and then you move here, there, and this is at a certain CB, at a certain level of CB of the temperature. You do this X trial and X current and so on. How many iterations we will do here? Keep in your mind, then this is the first chain, K chain equal to 1 here. And this is the first iteration of the technique. Now here at this level of the temperature, how many trial solution we will generate here? And you have to limit also this. For example, 100 iteration or 100 trial solutions will be created, and until you reach to thermal equilibrium, until we reach to thermal equilibrium. To go down, if we reach to thermal equilibrium, then we go down to another level of CB. We multiply CB by mu, so we have another level of CB. And here, for example, this is the current solution. At the end of the 100 iteration, this is the current solution. So we have this current solution, and then at this level of CB, then we can start creating current solution, trial solutions, and move here and there until we reach to thermal equilibrium. So if this current solution, if we reach 100 iteration, or this current solution doesn't change for 20 iteration, for example, then this is the current solution at this level of the temperature. So we go down by cooling. Again, we have now mu times the value of CB here. So we have another level of CB, and then with the current solution, we start creating trial solutions here until we reach the thermal equilibrium. This is the thermal equilibrium. Thermal equilibrium is reached either by hitting the maximum number of iteration you set, or the current solution doesn't change for several iterations here. So check the equilibrium condition. If the current solution doesn't change for a certain number of iterations, or the maximum transitions at this chain have been done, and you reach the maximum number of iterations, you set it earlier at the beginning of the code. You have to set, you can think now, Nasser Hakami, do you have a question?
Yes.
Nasser.
Yes. So looking for equilibriums, it means that we have to look for the all initial population, yes?
Initial population?
Yeah, in the beginning, we have initial population we are creating.
We have initial solution only.
Only one solution.
There is no population here. This is not population-based technique. As we mentioned, simulated annealing is a local search. You start with one solution, and then you create another solution, and either you accept it or you keep it, the current solution as it is. If you accept it, then you move and you generate another trial solution, and you compare, and either you accept it, or if you accept it, then you move. If you accept it, then you move, and so on. Okay? So this is not population-based. This is local-based technique. Is it clear, Nasser?
Yes,
this
clear.
Is also one difference between the genetic algorithm, differential evolution, evolutionary programming, particle swarm. This is population-based. And simulated annealing is a local-based. You have only one solution, and then you create another solution, and so on. So these are the thermal equilibrium limits or criteria. And then you, if you reach to the thermal equilibrium, the next step is to what? Any answer?
Decrease CP. Decrease CP.
Decrease the temperature. Multiply by mu, and you set mu at the beginning. Mu is a constant equal to, for example, 0.95. So whatever temperature here, you multiply by 0.95, you have another level of temperature. And then you create again and again. So you have the current solution, but now with different value of the temperature, and then you have you create a trial solution, and then you move here and there until you. If it is satisfied, and if the thermal equilibrium reached, then you go to step 8. Else, go to step 5. And create another trial solution. And then you update, or you skip this if the solution is this solution is still better than what we found, and then you back and forth until you reach to thermal equilibrium. If you reach thermal equilibrium, then you go to step 8, which is the cooling. Step 8, okay, stopping criteria. You check the stopping criteria. The stopping criteria here is similar to what we have earlier in particle swarm or so. If the maximum iteration reached, خلي بالك ان we have here two kinds of iterations. One iteration is counted on the chain. This is chain number 1, this is chain number 2, this is chain number 3. So we have here maximum number of chains. And we have also maximum number of iteration within the chain. So you have here maximum number of iterations within the chain and the maximum number of chains. The stopping criteria, the global stopping criteria here for the search is to check K chain. Check the, okay, this is the step number. We have here the stopping criteria. The search will terminate if one of the following criteria is satisfied. Number of chains, since the last change of the best solution is greater than a pre-specified number, and the best solution doesn't change for a number of chains, and the number of Markov chains reaches the maximum allowable number. So it is similar to particle swarm. If either of these criteria is not met, in this case you go and do the cooling, and you have here either you increase the number of chain by 1, and you also decrease the temperature by multiplying, and then you go to step 5. Step 5 will create a trial solution, and you compare with the current solution back and forth until you reach to this. If one of them is satisfied, then you stop, and you have now the optimal solution. So, Muhammad Tahir, Sabah, please.
Yes, doctor. What is the typical value of alpha?
Alpha is 1.1, for example.
Okay.
Or 1.1 to 1.5, let us say. 1.5 can, it's okay, it will not harm. You will reach temperature high, but the cooling schedule will be slow. And again, you may multiply by 0.5, so you increase the temperature higher than needed. So when you cool down, this will take like, some steps, more steps. But this is the range, and the mu also is between 0.8 to 0.99.
Yes.
So typically 0.95 is a good compromise.
Thank you, doctor.
Okay. Fauzan?
Yes, doctor. Here, is it a one heating up and then start cooling, or
it's not one heating up. No, you have heating up also happened in steps. Here, yields you multiply by alpha and go back to step 2. Go back to step 2, and this is step 2. You create 100 solutions, for example, as a trial solutions. And then you check how many solutions will be accepted. How many solutions will be accepted. If you reach 1, then you skip the heating up. If you don't reach 1 or very close to 1, let us say 0.99 مثلا, if you don't reach this, you have to go back and increase the temperature and go back to create trial solutions and so on. So the only way to escape from the heating up is to find the acceptance ratio is very close to 1. That means you reach to the melting point of the metal.
Yeah, that's what I'm trying to say. Yeah, that's what I'm trying to say. The looping here is only to gradually increase the temperature until you reach the equilibrium. Once you reach the equilibrium, that means now you start cooling.
Once to reach this, and the acceptance ratio is very close to 1. Why we are heating up? You don't know actually from where we can start CB0. Maybe some, you can say, مثلا, I don't want to skip, I don't want to heat up and do extra iteration. I will put مثلا CB0 equal to, for example, 1000. This 1000 could be very, very, very high. So when you do cooling down, you have here very high number of iterations, and you still cannot escape from the current solution. And you have here extra steps without needing to this. يعني if you think about the physical annealing, until you reach to the melting, خلاص, this is when you reach the melting, then you start cooling. It is not necessary to heat it up again and again and again. It will not, it's just consuming time. Is it clear?
Yes, yes.
It's better to start with very small value of CB0, and you heat up until you have this acceptance ratio is approximately 1. If you reach to this, this is the starting cooling procedure here. So this is better, of course, compared to having a very high number, and you don't know whether maybe this very high number even could be not it's not maybe you can say no, 1000 is very high, but maybe it is not very high for some problems, and you may need to heat it up again. هو حتى in physical life الميتالز has different melting point. Okay, is it clear, Fauzan?
Yes, yes.
Okay. So this is the parameters, the number of Markov chains. This is the stopping criteria of the search. The maximum number of transitions in each temperature level, in each chain, a number of trial solutions that will be created in each chain. The acceptance ratio, you have to set it also 0.9, 0.95. You have to also select this at the beginning of the code. The heating up factor, the cooling down factor, number of intervals for neighborhood radius, and this is we already discussed this before. You have the range of each parameter, and you divide this range by number of intervals, so you can define the neighborhood in order to create the trial solutions. We start with the initialization of the control parameter here, alpha, mu, initial solution, randomly, which is the current also, which is the best also, and the acceptance ratio you have to set, and then you generate N1 trial solutions, and you check the acceptance ratio, count the number of accepted solution, and then you check N2 over N1 acceptance ratio. If it is satisfied, if it is not satisfied, then you need to increase the temperature again. So you multiply here CB by alpha CB, and then you go back and generate N1 and C and so on. So you are looping here until the acceptance ratio is greater than the value or very close to 1. So if yes, then you need to if yes, so this is the initial and the heating up step, and then we will start looping here and the cooling down step. If yes, we will go for the counter of the chain, and then we generate X trial, and we calculate the objective function of the X trial, and we compare it with the X current and see whether we can accept it or not. And we have two ways for acceptance. Either J trial is lower than J current, then we accept it right away. Otherwise, we have to calculate the probability of e to the minus delta E over CB, or the temperature or the control parameter here, and see. If it is accepted, if yes, then we set the current solution, update the current solution and the J current. So the current solution now is the trial solution. So we move from the old current to the new current solution. And we set X, طبعا the counter here of the X current equal to, or K current equal to 0. This is in order to check the thermal equilibrium. And as we mentioned, the thermal equilibrium for each chain will be controlled by either the number of the current solution doesn't change for a long time, or we reach to the maximum number of iterations within the chain. So we set K current equal to 0, and we update already the current solution. So we reset the counter here. Otherwise, if it is not accepted, then we set the K current equal to K current plus 1. So we increase the number of iterations that the current solution is still there. And then we of course, we check the best solution, whether it is J trial is lower than J best. If we have better solution, then we update. Otherwise, we go without update. If no, then we go without update. So we can say K best equal to K best plus 1. So then the best solution also, the number of iterations that the best solution doesn't change will be counted for the stopping criteria. And if yes, if the J trial is less than J best, then you update the J best, or you update the best solution. Update the best solution and reset the counter of this one, and then you go. Did you reach the equilibrium? If yes, then you move forward. If no, then you go back and to this point, and you generate another trial solution, and you see, and so on. So if no, then you have to go back and generate. If yes, then you start cooling down process, but you can check the stopping criteria first. The stopping criteria here based on the K chain, number of chains, if you reach the maximum, or number of the best solution doesn't change. This counter means no, the best solution doesn't change. So if you reach 20 or 30 iteration, 30 chains here without, then you can do this. So if yes, then stop. Otherwise, you increase the counter of the chain, and then you cool down the temperature, and then you go back and forth until you reach to the stopping criteria. So this is the flow chart of the simulated annealing. Do you have any question? This is some kind of, GIF that it can show you how the simulated annealing works. So you have here, if we start again. So this is the current solution, and this is the trial solution, and then you move here, and this is this is the current solution, and then you have here, this is the trial solution, and this is the trial solution. So this is the maximization problem probably. So this will be moved. Maybe this is acceptable, but this is better. This is the best solution here found so far. We create here the current solution, and you are moving here and there until this one becomes better than this one. So you update the best solution here, and then you create a trial solution. So this is the best solution here now, and so on. So this is the way it is done. And also I think about this. This is hopefully also give you an a clear idea about how it works. You have the initial solution here, and then you trial solutions you create in the neighborhood, and you move back and forth. with the current solution. If you accept it, then you have here created several trial solutions, but the current solution doesn't change. So in this case, you reach to the thermal equilibrium and you reduce the temperature, and then you move, again and again. Here we reach to the thermal equilibrium here, so we reduce the temperature, and then we move here. Thermal equilibrium, and then we will continue until we reach to the number of iterations CBN. It is less than, of course, and then you have here. So you generate several trial solutions, and the current solution doesn't change for a long time, but this is the optimal solution here. So this is how it works, simulated annealing. By the way, simulated annealing is a very efficient optimization technique. Yani don't underestimate its capability, or don't look it down. Yani it is very efficient, and you can try it in your research. Abdullah Yusuf, do you have a question, Abdullah?
Yes, Doctor. You mentioned that simulated annealing is local surface. So, what is the main advantage of using this technique? Because usually we are global push, not local.
Now we are giving you a wide spectrum of the techniques, Abdullah. We discussed the global optimization techniques, and we have also, as we mentioned, Abdullah, for this, we just discussed it in a few minutes ago. Sometimes it's very difficult to start randomly over the search space with the global search techniques. And global search techniques, you can stay for long time, hours and hours, days and days, in order to create a feasible solution at the beginning. And to find a feasible solution, it's very difficult if your problem is very complex. Okay? And you can have only one solution feasible, and then you move forward. And this is also, it has some merits. And although it is a local search, but it has some merits. And you can find a certain application that simulated annealing is much better than the others. Okay? ماشي يا عبد الله.
Yeah, you mean we use it as a part of another technique, or we combine it with other global technique. This is what you mean?
You can do some kind of hybridization, and you can hybridize. And for example, hybridization of the techniques. You can say, okay, I will start with genetic algorithm. I will run genetic algorithm. I will end up with the optimal solution here of the genetic algorithm. And I will start the simulated annealing. I will take this as the current solution, and I will try to search in the neighborhood of this solution. Hopefully, I can obtain higher quality solutions here. So this is simulated annealing, and definitely when you search in the neighborhood of this solution, then you can find a better solution. So you can hybridize this simulated annealing as a local search with a global search. This is not only the one way to hybridize these techniques. You can hybridize it in more intelligent way. You can say, okay, this is a genetic algorithm. I will start with different solutions here. I will not use these solutions right away, but I will apply simulated annealing in the neighborhood of this solution. I will search in the neighborhood of this solution to better solution than this. And also I apply simulated annealing here. And this is the out of simulated annealing, this will be the initial population. And then I will do crossover and mutation and so on. I have another. I will apply simulated annealing here to search for better solution and so on. There are a lot of ways to hybridize, but of course, with hybridization, you can get to higher quality solutions.
Yeah.
Yeah, Abdullah?
Yes, clear. Thank you.
Okay, welcome. Nasser Hakami, please.
Yes, Doctor.
Yes.
One slide before.
One slide before.
When you are saying that for the curve after, yes,
Okay.
we're saying this, the particle is moving from around the neighborhoods. Mean at the certain CB, yeah.
Yes.
So in other example, this is heating up. The CB for us is the temperature control. But if I am looking for maximize of any functions, minimize the CB, there's the controller. This mean like the K and T1 and T2 are variables controlling that one, or how I am moving from a place to another place, because the neighborhood is so limited that when I move around the same place with the certain 10% only of the divided by n 10, it means 10% I'm moving around. So maybe I will be trapped only in one place. So how I am moving from to the extreme left to the extreme right.
لا يعني هو طبعا this يعني this example يعني don't say انه مثلا انه how to move from this point to this point. This is very huge يعني jump.
Yes.
Okay, this is what you are asking about.
Yes.
This is okay. يعني this is just an illustrative example. This is just an illustrative example. يعني as we mentioned earlier, إنه you define the neighborhood. You define the neighborhood. D equal to D مثلا in terms of K equal to K max minus K minimum
over 10, for example.
Over 10. By the way, this 10 is a key parameter. And maybe 10 is very low, and you need to, of course, you need to trial and error. But if assume that we have 10, and if you have a particle here or the solution here, and this is the, for example, this is K minimum, and this is K maximum. You divide this to 10 intervals. So if you have any solution somewhere here, you allow this solution to jump up to this point. طبعا مش لازم ياخد الجump كلها او الراديوس كله، انما within this you can generate a trial solution here or here or here or here, and then you move forward. Maybe حتى even if the trial solution is not better than the current solution, you still can accept it, and then you move forward here and there and so on. So this is just an illustrative example how it moves. And you have here one solution and you create a trial, and then the trial is best, then you go up here and then you, and so on. Is it clear, Nasser?
Yeah. Yes, Doctor, but how here the decay is changing, because I'm moving from either right to the left only a 10% of the whole space. So, and then how I move after, for example.
This is the maximum. This is the maximum. Let us go to how to generate the trial solution here.
Yes, in this slide.
Yes, this one. This is how to generate the trial solution. Okay, and you have here range of k, so you can get and you divide by 10 as you mentioned. So this is the maximum. So the trial solution will be equal to x current plus d, and d has a random number. So this random number may be 0.5. If it is 0.5, then d equal to 0. So x current هو نفسه x trial. If r equal to 0.7, then this will be 1.4 minus 1, so 0.4 times the d maximum. Okay, and then you add to the x current to the gene here, and so on. So you can move either way, positive and plus minus, but between 0 and d max. D, jump of d here, when you create d is between minus d max to d max. It's not necessarily to be d max. Is it clear, Nasser?
Yes, Doctor, clear. So in this example, the d max for us is a 10. So I'm moving either 10 to the right or minus 10 to the left, is mean. But
it's not
how I move
10. It is not necessarily 10.
10 or below.
Or below, yes, okay.
Yeah, but I mean, how can I, if it is my solution, for example, the k is 30, then I am allowed to move until 40 or 20. But how can I move to the 60 and 70 and 80?
Oh, this 40 will take you again, and you have here a current solution. This is its current. And then you get here, and you are moving to the better solution, right? And if the better solution here at 60, yeah, but you have this is x current, and then you have x trial. X trial is better, so this becomes x current, and you remove this, and you within this bounds you generate here x trial, and you generate x trial, and whether you accept it or not, this is 100 times. So this is x trial now, and you compare it. This is better than this. You eliminate this, and you consider this as x current, and then you move, and so on. So
okay.
you reach, but maybe you reach after 10 iteration, 20 iteration to that level. Okay?
Okay.
Did you get the point?
Yes, I get the point, Doctor.
Okay. Any other question?
I have one question, but not related to this topic, another topic.
Yeah, okay, go ahead.
It is related to differential evolutions. So, which better, doctors, to generate about initial population of, for example, 10 solution, and then I make iteration 100 for each 10 for each run, for example, similar to the homework, or I make 100 population and then I make 10 iterations.
Well, this is this is of course I would like to say, you have to compromise. If you have, this is the search space, and you generate 100 solutions randomly here, and you move to with 10 iterations, you will not here implement the concepts of the differential evolution for a long time. You are close to what we can say in random search. more random search كده. We generate solution, and we check it, and we generate another, and we check. We can take it. We can generate 1,000 solution here, and we check which one is better. So this is a random search. So if you generate 100 solutions and for 10 iteration only, this becomes very close to a random search.
Yeah, but what I mean, at the end, I'm making 1,000 evaluation for objective functions. So either I'm moving my particle by particle swarm, evolutions, crossovers, So I'm changing my solution to another solution. So I'm creating at the end 1,000 objective. So this is giving me 1,000 objectives. This one gives me 1,000 objectives.
A number of objectives, yes, they are equal.
Yes.
But probably the quality of the solution at the end of the 1,000 evaluation, the quality of the solution.
So it means better to go with the 10 populations with more iteration to explore or to get.
10 is in the low side. You are comparing between very far values, or extreme values. 10 is in the low side. 10 you will take a high number of iteration. Number of generation or number of iteration will be high to reach to the optimum solution. If you take 100, you will reach to the optimal quickly, maybe with lower number of iterations. But you can say no. You will not use the direct search of embedded in the differential evolution or embedded in genetic algorithm more likely here than this one. You have to compromise. There is no clear, but what the idea is clear. Don't make the population very small. This you may reach to not high quality solution, and the iteration number will be very high. If you have high number or high size of the population, so this will take more time. You will reach to the with less number of iteration definitely, but it will take high time in computation for each iteration. And these are some guidelines, general guidelines, but
because what I noticed, Doctor, in homework for the 10 runs, if I increase the population, one times it reduced the number of iteration for solving criteria. That was acceptable. But sometimes if I increase too much the population, our objective function is not getting better. Sometimes it's getting worse.
This is what I just told you. No, if you start with 100 iteration, 100 solutions, and then you do very few iterations, in this case you may reach to immature solutions. You didn't implement the direct search for a long time in order to reach to high quality solutions. This is
so in general, in general, we can say it's better for AIs in a method that we run many times, so that we can not only we increase the iteration, we should also run again and again until we get our best values.
This message exactly, that's what I want to give it to you. And with this, when I ask you to run it several times with different mutation probability, with different crossover probability, and so on, you can see how the search will be affected by these parameters or these key parameters. So as you observed here, we have to run it several times, and we should have also some statistical analysis for each for these several times. What is the max? What's the minimum? What's the average? And how the the key parameters affect the solutions. But this is what I want to say to you. And for such techniques, you have to
change the key parameters.
Change the key parameters and run it for several times until you reach to good solutions.
That's what we did. Okay, thank you, Doctor.
Welcome. Any other question? If there is no question, then you can leave and have a nice weekend.
Likewise. Thanks.
Thank you, Doctor.